Hi everyone, my name is Michael Lamb and I'm a professor at the Rochester Institute of Technology. And today I'm going to talk to you about galactic acceleration with pulsars. In some work that I did with Sarah Vigland, who's a part of the Nanograv collaboration, some people here at RIT, University of Wisconsin-Milwaukee, and also the University of Rochester. And so I know this is a little bit of an unusual format, but these are a little bit of unusual times, so I decided to give you an actual chalkboard talk. My apologies for the messiness of the board, but it is what I have, and so here we go. So in general, when we measure pulses from pulsars, we have a pulsar that's spinning around, and as it spins around, pulses are coming towards us here at the Earth. And so we have some telescope here at the Earth, and the telescope is on the Earth, so that means that the Earth is rotating around. The telescope is moving its positions, and therefore when we measure the pulses to arrive at our telescope are going to change. So we need to take that into account in any kind of timing modeling that we're doing. The Earth is of course moving around the Sun, so there's some orbit around the Sun. For many, not all, but many of our pulsars, the pulsars are also in a binary orbit with a companion. So there's some companion object here as well, and both of these are rotating around one another there. All of the objects in the galaxy are moving with respect to one another. So the Sun is moving in some direction through the galaxy, and then the pulsar companion system is moving in some direction through the galaxy. And so the distance between us and the pulsar is changing. Where it looks on the sky is changing. All of these things are coming into effect. We need to take these into account in a basic timing model. Okay, the ones that we selected, the pulsar systems that we selected for this work are those that are in binaries, and not only those that are in binaries, but the special ones in which we can measure something called PB dot, or namely the binary period and the derivative of that binary period. So that means that not only are the pulsar and its companion in an orbit with respect to one another, those orbits are actually changing. They're actually shrinking in size, and the orbit is typically speeding up. And there's a lot of things that come into play into an observed PB dot here, namely that we have intrinsic effects due to physics inside the system, and we also have effects outside of the system that make it appear like there is a PB dot. So probably the most famous of these effects is due to gravitational radiation. So in the Hulse-Taylor binary system, Hulse and Taylor, they discovered indirect evidence for gravitational waves by seeing that the orbit was shrinking, or put another way, that PB dot was increasing over time. And that increase was actually consistent with general relativity, the predictions from general relativity. And so we can write that as some term here, PB dot GR, for general relativity, the general relativistic correction, and that depends on things in the system, including the mass of the system, so both the pulsar mass and the companion mass over here. We need the binary period, and then also the eccentricity, so how elliptical the system is going to be. All of those things come into account, but if we assume that GR is correct, and we can measure these different things, well, we can measure the period of the binary, because by definition they're in binaries, and so we should be able to measure the period of those. Then, as long as we can measure the masses and the eccentricities, then we can calculate this exactly. No problem there. Okay, so that's one of the intrinsic terms that would come into play here. Another intrinsic term that could come into play is if there was some kind of mass transfer between the companion and the pulsar, or if the pulsar is ablating away its companion, so mass is being transferred out of the system, in which case the angular momentum of the system is changing, and therefore there's a PB dot just associated with that. Now those are very messy systems, so we don't actually include those in our analyses, because we can't actually know we can't disentangle what the intrinsic effects are going to be between the mass transfer and what we observe and some of these other effects I'm about to talk about. So they're just too messy. Okay, the other two effects that I will talk about, though, one is there's a term called the Shklovsky effect, SHK here. And that just depends on how the pulsar is moving across the sky with respect to us. Now, if it's in a binary, the binary period appears to change to us just because of that motion. So it's not an intrinsic change at the source, just here at the observer. And so that will depend on things like the distance to the source, so the distance, which we can measure from the parallax. It depends on the proper motion, so how it's moving along the sky, how fast it's moving. And it turns out that it also depends on the binary period of the system. Okay. That's all known because if we can measure the astrometry of the system, and we know what the binary period is again, then we can measure what the Shklovsky effect is going to be. Okay. And lastly, we have a term here that is related to the galactic potential. And so this galactic potential term is just saying that because the pulsar binary system is sitting in the mass of the galaxy, it experiences an acceleration, and that acceleration in turn causes an apparent PB dot on our system. So again, not actually intrinsic to the system itself, just because there's an acceleration pulling on the binary system itself. Okay, and that acceleration is going to be related to both the binary period and the acceleration due to the galaxy. And I apologize, now I'm curving all the way over the place, but that's how it goes. And so, if we can measure this term here, so we can observe the period of the binary changing, if we know the astrometry of the system, and we know the masses and the eccentricity of the system, or if this is a really, really, really small effect, so for example, if the eccentricity is 0, then that's not going to be important at all. If we can measure all of these other things, then we can measure the PB dot due to the galaxy, or in turn, we could measure the galactic acceleration down here. And that's exactly what we've done in this work. So we've inverted this equation, and we said, let's figure what this is, depending on what we've observed, and then these two estimators here. Besides systems where we have removed mass transfer systems, so any systems where mass is moving, sloshing back and forth, we've also removed systems that are in globular clusters, because in that case, not only is there a term due to the acceleration of the galaxy, but there's also a term due to the acceleration inside the globular cluster, which can be very, very, very high. We've also removed systems where there's no astrometry, so sometimes you can measure PB dot in early observations, but we don't have good astrometric parameters, in which case we don't know what this term is, the Shklovsky term, and so we can't say anything about it. And then we've also removed systems in which we don't have uncertainties on these parameters. So sometimes these are reported in the literature, but there's no uncertainties on them, and so we just decided to throw them out. And so what we're left with are 14 different pulsars that we use in our work, and that's not including the Hulse-Taylor system itself. And the problem with the Hulse-Taylor system, it's not actually a problem in it of itself, is that it is very, very far away compared to all of the other pulsars. So I'm going to put a map of our pulsars at the end of this video, but you can imagine that if I had a top-down view of the galaxy here, and so here's the Galactic Center, and let's say here's the sun, all of our pulsars that we're using in this experiment kind of fall around in here. And the Hulse-Taylor system is sort of out here. So it's a couple kiloparsecs away. And so because we have a lot of information around here and only one point over here, we can't really say much. And so we've just decided to ignore it in this work. In the future, if we get lots and lots and lots of pulsars, either at farther distances from us or in higher galactic, higher in the galactic plane, then we can use this information going forward. Okay, so how do we do this kind of modeling? So we have our pulsars, we have our scheme of what we want to do. How do we do the modeling? Well, we looked at a number of different potentials for the galaxy, and those potentials determine what the acceleration is going to be. And because we just have the PB dots here that we observe, really we measure a line of sight acceleration. So we don't measure the full three-dimensional acceleration, just the line of sight acceleration, but if we know what the acceleration is going to be on a particular object, let's say at some distance r from the galactic center, and if I look at the galaxy edge-on, and so here's the galactic center, if I have an object up here at some height z, I can figure out what the acceleration is going to be in the r direction and in the z direction given some potential. So for example, the simplest potentials that we look at are static potentials, in which we can separate this potential here into two parts. So in general, it's related as a function of r and z, the radius from the galactic center and the distance from the midplane. But we separated these into two terms, so an r term here plus a z term, so totally separable, like so. And we fit a bunch of different parameters that go into each of these terms. So for example, in our paper, there's one term here that's a beta, and then this in z is a polynomial expansion. So we have what we write as alpha 1 and alpha 2. And we can test and see, okay, which ones of these are significant. If we hold beta equal to 0 and set these other ones to some value, what are those? And we go through a whole model selection process. And what we find at the end is that the most preferred model is the one that only has alpha 1 in it. And this alpha 1, in terms of an acceleration, is just a linear relationship with z, or namely that the acceleration of that term is equal to alpha 1 times z. And so for reference, the value that we get out of this is, approximately speaking, that alpha 1 is equal to 5,000 inverse gigayears squared. Okay, so that's a weird unit, but if I had z in kiloparsecs, let's say, and alpha 1 is in gigayears, inverse gigayears squared, then I would have units of kiloparsecs per gigayear squared, which is something related to what we also always think of acceleration as in terms of meters per second squared. Okay, so that's the value that we get out of it. That's the best fit value from this modeling. We do look at other potentials that are more complicated. So for example, we look at some where there's an oblateness term in the galaxy, so it actually combines the effects of both r and z. We look at other people's models. The one that we find that is most constrained by the data, which is pretty, in my opinion, it's not great. We only have 14 pulsars. The errors on PB dots can be high. And in fact, the biggest term of uncertainty are the parallaxes and proper motions of these systems, typically the parallaxes. For some of the systems, in fact, there's no timing parallax, or there is a timing parallax and it's very poor, but other people have gone out to look at VLBI measurements of these systems. Okay, and so they're able to get the astrometry that way. Okay, so these are the results that we get out of it. We can also look at what the density is of the midplane, or namely how much mass there is in the midplane of the galaxy along here. And what we find is that there's some mass that we can get out of it, and we can compare that mass with quantities of baryonic mass, so from other estimates, namely from stars and other gas. Then other authors pull that together and they say, here's the amount of baryonic mass. And so we can take our total mass and the baryonic mass and we can subtract that to get just what the dark matter density should be around the sun. And the value that we get out is not terribly constraining. In fact, that dark matter density is between 0.05 solar masses per cubic parsec and unphysically 0.02 negative on the other side here. So this is consistent with 0. It's consistent with other estimates, but not very constraining, unfortunately. But it is a direct measurement that we're able to do, and hopefully in the future, with more pulsars, and especially more pulsars at larger R separation, so either more negative or more positive, farther or closer away from the galactic center, or at larger Z separations, then we'll be able to make more statements. Okay, so the last thing I want to say is, why should pulsar timers care about this besides, okay, this is a very neat thing? Well, in this modeling, we can invert our equation for PB dot observed, and instead say, okay, I have an observed PB dot, one of the things that pulsar timers do is say, what is the consistency with general relativity? So instead of assuming that general relativity is correct, they actually go look at what the constraints say about general relativity. Well, in order to do that, we again have these terms. So we have the GR term here plus the Shklovsky term plus the galactic acceleration term. In our work, we assume that GR is correct, which is a pretty good assumption. It's pretty close to correct. And we fit for what the PB dot of the galaxy is. In other works, they assume some values of the PB dot of the galaxy, which are not necessarily consistent with what we're measuring from our 14 different pulsars. And then they're inverting the equation to solve for PB dot GR here. Okay? So this modeling can actually yield potentially more unbiased constraints on what the local PB dot of the galaxy is going to be near the sun, which is where all of our pulsars are that we are observing, and then we can use that to better constrain PB dot GR. And this PB dot GR shows consistency with gravitational radiation. We have used it in nanograv and other collaborations to help look for changes in other post-Newtonian parameters or alternate theories of gravity. So for example, looking at the change or the rate of change of the gravitational constant, so G dot. And so for all of these different tests of gravity, knowing what the galactic acceleration is going to be is very, very important. And so going forward, one can imagine that we can use this kind of analysis to, from the data, pull out what the galactic acceleration term is supposed to be, and then use that to constrain our theories of gravity. Thank you very much for watching my talk.